Okay, so I shouldn't take away from your research that we're going to go to the moon and find like a T-Rex skull.
You're listening to The Cosmic Cast.
Hello and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. Your regular host today, it's me, Marissa Lowe, joined by John Pernay-Fisher.
Hello.
Tom Harvey.
Hello.
And our special double bill of guests today, it's PhD students Sam Halim from Birkbeck.
Hi.
And Zoe Morland from the Open University.
Hello.
Hello, and thank you for joining us today. So I guess we've invited you both on today because both your PhD projects have quite a few similarities between them. You both research impacts.
Yeah, we do. They're pretty similar, I guess. I research impacts into the lunar surface, and Zoe, similar, but to do with
Mars and Phobos, so they're closer moon of Mars.
Amazing. So yeah, I guess we've touched on impacts in quite a few podcast episodes. They're obviously a very ubiquitous process throughout the solar system. But yeah, what's interesting about studying impacts then?
I think it can just be the beginning and the end of everything. So
we've started very deep there.
I think it can bring life, it can provide the conditions for life to start, and then can destroy everything altogether, or transport something that's in one place to somewhere else. So it's just the mechanism for everything to begin and end, I think.
Yeah, I mean, I agree. Also that because they're so ubiquitous throughout the solar system and beyond, they're the most easily comparable aspect of any planetary body. Mm-hmm. And so there's such an easy way to, if you have a surface and an impactor, you're going to have impacts and something to compare between Mars, the moon, Earth, anywhere across the solar system.
Okay. So what is it specifically about impacts that you guys study then?
So personally, my impact studies are to do with, at the moment, terrestrial meteorites into the moon.
Oh, cool! Yeah, I guess that's quite a hot topic at the moment, isn't it?
Yeah, I mean, in part, yeah. My part of that is looking at numerical modelling. Mm-hmm. So I use a code called ISAIL, which is a hydrocode which models these physical interactions between materials of differing strength and different compositions, and seeing how they interact to form these impacts on the moon.
Amazing. What about you, Zoe?
So I'm looking at how impacts can deliver something to somewhere else. So it's sort of this broad idea of lithopanspermia, where life in any form can be transported in a rock from one planet to somewhere else. And the idea that if Mars in its early history was habitable and may have developed life, that biomarkers may have survived on the surface, and that these biomarkers could be transported in impacts. So if a large impact were to occur on Mars, ejector material, including these biomarkers, could be ejected, and that this material can go anywhere. So of course we see Martian meteorites here on Earth, but these all tend to be basaltic, and of course they've had to have survived much worse than just transporting from a short distance, and having to go through the atmosphere is a big step. Whereas the material could just go up through the atmosphere and land on the closer moon, Phobos. Mm-hmm. And this is just a tiny asteroid-like moon with no atmosphere or anything on the surface. So it could act like almost like a fridge for any material landing on the surface. It could then just stay there, and the only thing it's exposed to is just space. So nothing living would be there really, but there could be biomarkers which give some kind of indication of what life could have happened on Mars originally. Yeah.
That's really cool.
What are biomarkers, like chemically or physically?
So I think for me, they vary. I think biomarkers differ. They're just anything that can indicate life. Do you have a better definition for a biomarker, Sam?
I mean, I'd agree that it's anything that can indicate the presence of life once being there. So in my case, in looking at the transfer of terrestrial material to the moon, I'm looking at biomarkers like amino acids, or something like lignin, which is a larger molecule that helps in the formation of cell walls in plants or in wood or trees. So anything that can indicate there was once present life at the original surface that the asteroid or meteorite has come from. And this can be, chemical composition. It can be in many forms, as long as it indicates that life was once there.
That's cool. So I guess these biomarkers, were they quite sort of robust then to things like shock and impact processes? Or I mean, would you expect to find quite fresh signatures, or would there be a bit of detective work to figure out if these things are still being preserved?
Well, they're definitely more robust than, say, a fossil or a microfossil.
Okay.
From what the research that I've done so far in these terrestrial meteorites impacting the moon, you're looking at things that can survive many hundreds of Kelvin and many tens of GPa of pressure. Especially for certain amino acids, you're looking at things that can survive up to 70% of their original mass.
Oh, really?
21 GPa, yeah. And some of these things can survive temperatures, at least these flashes of temperature from shock heating, for very short periods of time, but they're very high temperatures. They can be 2000 degrees Kelvin, but as long as it's just a flash of a second, you're looking at relatively good survival for these kind of robust amino acids or.
Well, that's really cool. I wouldn't have imagined that. I would have imagined they would have been quite fragile in space. That's awesome. Yeah,
at least in modelling, obviously there's a kind of a big discrepancy between what models predict and what actual mechanical impacts can see, and I think that's where the differing parts of our projects become apparent in the fact that I'm looking at these larger scale yet modelled materials, but these smaller scale actual materials that are being fired into other things is what Zoe is fills the gap at least.
Yes. That brings us on quite nicely. We've mentioned, Sam, that you take a modelling approach to this, whereas Zoe, you take a more experimental approach. Would you mind talking us through what experiments you've been doing to research this?
So we, at the OU, we have what's called the all-axis two-stage hypervelocity gas gun. And so what this is a modified shotgun which combines two stages, one being the ignition of gunpowder in a similar way to a normal gun, and then the second stage being the compression of a light gas, which is normally hydrogen, and the compression of the light gas allows for a much higher force to be produced behind the projectile. So that fires a projectile normally up to about 3 millimeters in size, down a gun which is about maybe 3 meters long, into a target at speeds of up to about 7 or 8 kilometers a second. That's what we can reach. And then we can fire into a solid object, so we can do that horizontally, or we can remove the floor, allowing us to make the gun vertical, allowing us to fire into liquids or loose material. And that's what I'm going to be doing in my project. So my project uses a Phobos regular simulant that was designed to try and figure out in these experiments whether life could be transported from Mars to Phobos, because the idea is that there's planetary protection which governs how we explore space. So Mars is protected by planetary protection, which governs that any mission that goes there has to be sterilized in a particular way, so we don't forward contaminate anything, so we don't take anything from Earth to contaminate any potentially habitable environments on Mars. And then also that anything we pick up from Mars and bring back doesn't just saw that cat.
Have we got another guest coming on?
Yeah, I knew it would happen. I'm sorry. It's my
Quite
one
all
of my
right.
cats creating
We're,
a lot of chaos, apparently. Come on.
Cats are a friend of the Cosmic Cast.
I'm so sorry, Zoe. You're
Don't
on a
worry.
roll.
Yeah, so you have this forward and backward contamination. So if anything we pick up from Mars and we bring back, which is a potential for doing sample return,
Mm-hmm.
that anything there doesn't contaminate the life that we have on Earth. So the idea is that if material could be transported from Mars to Phobos, whether if enough material has done that, whether we should treat Phobos in the same way as we treat Mars.
Mm-hmm.
So whether it should be planetary protected. So there's a mission that's flying in 2024, in theory, from JAXA,
Mm-hmm.
called MMX, the Mars Moons Exploration Mission, which is designed to go to Phobos and collect material and bring it back. And if there's the chance that there could be enough material that's from Mars originally on Phobos, then the sample that could be collected could contain things that could be potentially harmful to Earth. So back to this Phobos regolith simulant that was designed. So this was designed to run these impact experiments to see whether live organisms could survive impact from Mars to Phobos. And the results of that were basically inconclusive, saying that it could be possible, but it may be unlikely to reach the percentage that is required for planetary protection. And that means that Japanese Space Agency don't need to spend many, many more millions of pounds trying to sterilize their equipment more. But there's still the chance that when they bring back the material, it could contain Martian material and therefore biomarkers from Mars. So yeah, so I use this Phobos regolith simulant, and I'm going to be firing biomarkers into it to simulate the process of material transfer from Mars to Phobos.
That's very cool. So
Yeah, that's awesome.
How representative is that sort of velocity for I guess, Mars escape velocity? Is that pretty much bang on from the gas gun?
Yeah, I think anything up to the maximum of the gun is good. It actually varies. So when ejector leaves Mars, models like Sam runs have shown that actually the more likely material to land on Phobos is material that has been ejected from Mars and then is returning back to Mars again. So it almost falls on the top edge of Phobos.
Mm-hmm.
And this means that Phobos could collect the material in any way. It could collect it as Phobos is orbiting around, or it could come up underneath it, which is the original ejector material, or it could slowly land on the top of it. And this means that the velocities of the material landing on the surface vary hugely. It could almost technically be zero if you think that Phobos and the material are almost moving at the same speed. So it varies a lot, but I think it could be much higher than the speeds that we can simulate, and that's how you get meteorites on Earth from Mars. But thankfully it's within the realms of what we can, yeah.
That's very neat. So how do you fire these biomarkers then? Are they, is it just like a pure kind of little compound, or is it mixed in with a kind of Mars type rock material? Yeah, so a part of my project is trying to figure out how I can make these projectiles that have biomarkers in them. So previously what has been done is that they have a basalt or any kind of rock, and they've drilled a hole in, and then they've put in a liquid that has the stuff that they want that's biologically relevant. Whereas for me, I want to make a homogeneous projectile, because if you just drill a hole in and you put it in the middle, that assumes that everything's concentrated in the middle, and there are lots of complex dynamics around how material survives depending on whether it's at the edge or at the interior of the projectile, which Sam has done some work on. So then I want to make this homogeneous projectile, and that involves me getting some material and mixing the biomarker, which we come as a powder, and mix that in with a binder,
and somehow make a solid that I can then drill out the projectiles. But that's currently at the experimental stage, and I haven't managed to work that out yet, whether I can actually make a solid. So that's the first thing I'll be doing when I'm back in the lab.
So yeah, Sam, how does that work in your model then? How do you decide the properties or the heterogeneity of your projectile, and then also the surface that you're going to be firing it into?
So there's obviously limitations with what the model can handle. But in general, what you do is you define the composition of the amount of materials that you want to have in your model. So say for something quite complex, like if you're looking at two planets impacting each other, then you want a crust, a mantle, a core. So you use different materials for those different elements of the projectiles or of the asteroids or planets that you're hitting together. For me personally, because these bits of material that are coming off of the Earth, these ejected terrestrial meteorites, they're on the scale of centimeters to meters size. So we're looking at impacting what I consider you assume as a spherical projectile, impacting a single layer target, because the crust of the moon is so thick and the regolith of the moon is so thick, and the megaregolith, that you can only consider it as one material. And so we can consider the projectile as something like a sedimentary material, which might have more biomarkers than an igneous or metamorphic. So you think of it as something like a sandstone or a limestone perhaps. And then you'd impact that into what you could consider part of, say, a maria like basalt, or maybe a gabbroic anorthosite for the far side of the moon. And ISAIL has this library of materials that you can use with different compositions, and they've been computed from shock experiments like the ones that Zoe's talking about. And you take those materials and you take their shock properties and you put them into a computerized version of that, which follows how shock influences the density, the volume, the pressure changes, the temperature changes. And these are measured things that are then put into the model in something called an equation of state for that particular material.
So that sounds like, if you're thinking about the regolith, obviously that's a lot of different particles you're thinking of. How computationally intense is it to use this model, or is it quite easy to run?
It depends on the resolution you want to do. So say you want to look at how a crater forms. That's quite a low resolution thing to do, because you're only worried about the morphology and the way that this material escapes whilst being ejected or something like that. But if you're looking at something quite detailed, if you want to see the different variations in pressure and temperature like I do, you need quite high resolution so that you can have a much larger scale of these cells that the simulation is made up of. So the more cells you have, the more data you can get out, and the more accurate the pressure and temperature is. So say you're looking at something like the regolith and you want to model it accurately, like a quite loose material, you're going to need something that a strength model that can model this kind of material. So it's not amazingly accurate, because it only models one particular material, and it might model one particular aspect of that material. But it does bring out results that can definitely be compared to the real thing.
And I guess you could sort of test the sensitivity of all your different parameters and single out different ones to see what the effect is, I guess.
Absolutely, yeah. The beauty of it is that you can do it over and over again until it looks like something that you would expect from real life. And as long as those parameters that you're changing are reasonable, they're not ridiculous just to make the data look good, then they're definitely justifiable to compare to actual data.
Yeah. So how likely is it then that some of these terrestrial impactors on the moon would survive and be found? Do you think they should be quite common on the lunar surface?
I wouldn't say common. I'd say that there is a likelihood that there is some material that has survived being ejected from Earth and then landing on the moon, with significant proportions of biomarkers within them. But whether we're going to find them at any point is a much different story, because
I guess it's the sort of thing that requires like people's eyes on the ground, effectively, doesn't it? I suppose.
Absolutely, and eyes beneath the ground, because if these things are going to survive over a long period of time, we're talking millions, perhaps billions of years. If we're looking for some of the part of the record that the Earth no longer records, these need to not be on the surface anymore. Otherwise, they're going to be bombarded with micrometeorites. They're going to have
ground away into the regolith, I guess.
Yeah, cosmic radiation is going to destroy any kind of biomarker. So you need some sort of protected layer over that, such as an excess ejector from a larger impact, quite a distance away, or maybe even a lava flow over that ejector again. So it's insulated by an ejector layer, and then the lava flow comes over the top, giving another layer that doesn't affect the temperature of the material that you're looking for, but is further burying it with a nice thick, dense something.
How big of an impactor would we need on Earth in order to transport material to the moon? Would we be looking at something, say, the size of the crater that killed the dinosaurs, or would much smaller craters be sufficient?
I don't think there's much of a limit on it, but bigger is better.
Yeah.
Something like a 10, 20 kilometer diameter asteroid would be sufficient, I think. What I've been modeling recently is 50 kilometers impactors. And I'm starting to find these relationships between not only the size of the impactor, but also the velocity that they come in at, and how that affects the amount of material that is able to be ejected. And also, more importantly, in fact, the amount of material that's able to be ejected, but also at a low pressure, so that it's not being destroyed. These biomarkers aren't being destroyed on ejection. They need to survive both transports and both impact from the Earth, the transport, and then the impact on the moon.
Yeah, because I guess the atmosphere must be quite a big challenge in order to transfer material then, which is something I suppose you don't really have to worry about so much on Mars, as you said earlier.
Well, it is actually something I'm going to be taking into account. So Mars has a small enough atmosphere that it's less of an issue, but it is still there. So it sort of has the opposite to effect of a meteorite falling onto Earth, where you get this fusion crust. It sort of does the opposite as the material flies off. So the idea of my experiments are I'm going to fire an inert projectile into a Mars-like rock which has biomarkers inside, and then collect the ejector from that to try and prove what material is actually transferred into the ejector, and then ejector to flash heating to try and simulate what would happen as it goes through the atmosphere. And that's something that was done by JAXA. They did that, so I'm going to replicate what they did. And then this processed heated material I'm then going to fire into Phobos. So it's sort of going from each stage, going from where it was originally in the bedrock in Mars to landing onto Phobos. So it's there, but I think it's an interesting comparison between the Earth and the Moon. So with the Earth having a much larger atmosphere and causing more issues, but then of course the Moon being much larger, but then I don't actually know the answer, but is Phobos, I assume Phobos is much closer to Mars than the Moon is to Earth. I don't actually know the answer to that question, but it would be interesting to know the comparison between actually what's more likely, whether material would fall onto such a smaller moon, but because it's closer, whether that increases the likelihood. And then for Earth, because of the atmosphere, whether that takes away a portion of the material that's being ejected, but then the material is more likely to fall onto the moon because it's larger. So I
suppose an added complication as well is that I suppose if you're trying to preserve biomarkers, presumably we're looking at a period in Martian history where there may have been more water, maybe some different sort of more sedimentary rocks and some different geology available for things to be impacted and transported. I guess it must be quite difficult to constrain some of those parameters of early Mars.
Yeah, that's true. So of course we're looking at Mars in its very early history, sort of 4 billion years ago, and that means that it's quite a small window perhaps that these biomarkers could have existed and be preserved, but they're widespread enough. So the missions, the in situ missions that are now on Mars, they're finding sedimentary materials that have some kind of relationship to at least water flowing on Mars, and then maybe even showing some carbon-like structures. So I think that it should be widespread enough, hopefully, and even if it's just below the surface. So, for example, in a similar way to what Sam was talking about, that this material could have been preserved underneath the surface, and then a large impact would excavate it from beneath the surface where it had been protected from the exposure to space, and could then fall onto Phobos. But I think, Earth has got a much longer history of life being present to give much more material that could be transported.
But is that something you think about in the model, Sam? Are you thinking about Earth, present day Earth, or do you think back through Earth's history and think about, what would an impact however many billions of years ago look like compared to what it would do now? Or does that not affect it as much?
I think that's definitely relevant in my work, in that I've been looking at how we might preserve something on the moon that we no longer have a record of on the Earth. So because of our multiple erosional processes, we've got subduction, we've got a huge water cycle, we've got a pervasive atmosphere where it's very thick, very, very active. These things definitely make sure that a lot doesn't survive in the early history of the Earth. So if something's ejected and lands on quite an inert moon, we're looking at something that may not be recorded anywhere else.
Is there a specific time period in the early Earth that you think is most likely that these sorts of impactors would have occurred?
Yeah, but it's a contentious issue in that the late heavy bombardment could be a time where a lot of material had been flung off the Earth.
So this is about 3.8 or so?
Yeah, 3
billion years?
3.8-ish. But of course, it could be that this was a period of time where there was either a large peak of impacts, or it was a large peak to begin with and has steadily decreased, or even the sawtooth issue and the idea that giant impact frequency has gone up and down from the early history of the solar system. So I don't really like to put my name on any of these and say which one I agree with, because it usually leads to some sort of discussion that I'm not very comfortable with putting my hat in the ring on. But it's definitely an early period of Earth's history where there's likely to have been a higher frequency of these giant impacts that are more likely to eject and produce these terrestrial meteorites. And I think going back to how the atmosphere affects the amount of material ejected as well, that comes back to how big the projectile is as well. So if you've got a large impactor hitting the Earth and ejecting this material, it's also going to punch a massive hole through this atmosphere. And because things need to be flung off the Earth at over the ejection velocity, which is 11.2 kilometers per second, these can travel up through that hole that's been created relatively easily, as long as there's a large window that's been created by that initial impactor into the Earth. So that's definitely where size of impactor is more important than impact velocity of that same ejector of impactor.
Yeah. That's interesting. I hadn't thought about puncturing holes in the atmosphere. That's quite neat.
Yeah, I mean, there was a recent paper by Beach this year, I believe, Beach et al., that kind of explores that through mathematical modelling as well. Okay. How this hole may form and how likely it is for a ejector to escape through it.
Yeah, no, that's cool. No, so I guess the reason why I brought up sort of what sort of timescales you were thinking about, I guess, because I was thinking, because I suppose we've got some idea of what kind of biology and what kind of fossils were present throughout Earth's history. So just wondering how if that affects your decision in terms of what biomarkers you consider, whether you're looking back to say what was in the fossil record at 3.8, and are you thinking about like big stromatolites, or are you thinking about, I don't know, whatever weird creatures were wandering about at that sort of time?
I mean, it would be good to look at that kind of thing, but so far I've only looked at molecules really, and I've slightly considered some spores, some megaspores and some microfossils, but that's something that has been explored in mechanical modelling, in impact studies, but not really in numerical modelling that much, because putting a centimetre or millimetre size fragment of a microfossil or fossil into a model isn't very intuitive in the model's terms.
Yeah.
So it's not something that you'd be confident in modelling, rather than this bulk kind of projectile that then you can assume some sort of molecule was in.
Yeah. Yeah.
Okay, so I shouldn't take away from your research that we're going to go to the moon and find like a T-Rex skull.
I wish you could. Okay. And I'm sure I could model it, but I don't think it would be accurate.
if you've got some spare time at the end of the PhD, maybe just, play around.
Maybe.
I mean, that's the headline, isn't it? Life on the moon.
Well, the thing, do you remember the water bears? What were they called? That on the Israeli space mission.
Tardigrade.
The tardigrades.
Tardigrades.
Yes.
Yeah. So there was thoughts with Katie even mentioned this actually, that we could model a metal spaceship impacting the moon and see if they'd survive.
Yeah. Why not? Absolutely. Yeah.
That could be the life on the moon.
Yeah. No, that's. Yeah. Why not?
So
sorry.
I was just going to say, what sort of sample return missions would you need to test some of the hypotheses that these models and experiments are kind of coming up with? I mean, presumably, is MMX, is that going to collect material that would kind of help you kind of, would agree or disagree with some of the things that you're doing with the gas gun experiments?
So it's going to collect, it's got a little scoop that will scoop from the surface, and then we'll also take a core from beneath. So the main aim of the mission is to just try and understand what the composition of Phobos is and what its origin mechanism is. So whether it's a captured asteroid or whether it's an impact product, a bit like our moon. So I think basically taking material from the surface and also the subsurface, and when I say subsurface, I think it's only about the length of your thumb deep, but that's sort of going into what Sam said earlier about how material could be preserved beneath the surface. So perhaps this core lower down might be a more likely place to find biomarkers that are preserved. And I think because Phobos is so small, like a small sample, if you sort of think about it, it sort of gives you a much more representative idea of whether, like, that you could almost agree that that represents the entire moon because it doesn't vary that much across the whole surface. So just taking that one sample, if you get however much proportion, no matter how small it is, then if that's Martian, then you get what you need. Whereas I think for the moon, you've got a much larger area to cover.
I suppose it's a lot more heterogeneous chemically as well, potentially. I guess also in terms of Phobos, I guess you brought up these two competing different formation mechanisms. I guess that must be quite important. Do you have a sense, or do you have a preferred mechanism?
So the composition of the surface is interesting. So I think that it resembles an asteroid. It resembles a carbonaceous chondrite, but it's extremely dark and it has quite a high proportion of phyllosilicates, which are sort of the things that make up
clays, basically,
and clays. Yes. So the high proportion of that sort of makes a bit more sense for having some Martian material maybe on it. But then it's all the dynamics, so the orbit dynamics. So it orbits Mars perfectly aligned with its equator. So, and in a very circular orbit, and it doesn't really follow then being a captured asteroid, but it looks like a captured asteroid, and just everything about it says it's a captured asteroid, but the orbit dynamics doesn't work. So there was a recent, I don't know whether you saw it on online, but there was a story about Mars having rings.
Yes, yeah. That's made the headlines the past few days, isn't it? At time of recording, anyway.
Yeah, so the idea is that Phobos could be this repeated coagulation and then destruction of a moon. So for example, like it's degrading in its orbit, so it's getting closer and closer to Mars every year, and the suggestion is that within 50 million years it will reach what's called the Roche limit, which is where it will disintegrate because of the Martian gravity. So, and that could then produce a ring around Mars, and that then could correlate into a moon again, and that there's been this repeated process of every several 100 million years of this moon formation and destruction. So there's lots of contention as to whether Phobos could be quite young. So yeah, there are lots of problems there, and I think MMX will sort out those issues when it goes and collects some material.
That's
So
so cool.
Yeah.
Oh, sorry, that I hadn't seen that. That is really cool.
Yeah, it's a neat hypothesis. That'd be amazing to watch happen.
yeah, if we could just speed up time a little bit.
Alternatively,
It's like almost within, like it's within geological timescales. It's quite recent, really. If you think within 50 million years it could be destroyed, I mean, it's really not very long. We've got to get there fast.
Yeah. Team that did the Planet series, their graphics team needs to get a hold of that idea, because that would look fantastic.
Yeah. I guess what's interesting about that then is that presumably it gets smaller and smaller during each episode. I don't know.
It's not very large. It's only, I worked it out as is the distance between, I mean, it's only if you know the area, but it's the distance between Milton Keynes and Bedford. Right. So it's only about, it's tens of kilometres. I think it's only about 15 kilometres wide. So
Phobos.
Yeah.
Okay, that's cool. That's really small. I hadn't realised how small it is, because I suppose I guess so. For comparison, then the moon, for the listeners, the moon is about the size of North America, isn't it? I think so. Yeah, going from that to basically the size of Bedfordshire, that's that's quite a step down in scale, isn't it?
Sizable difference.
That's neat.
So what's next for both of you for the rest of your PhDs then? I guess, Sam, you're quite happy chucking away at home, but I guess, Zoe, you might have had a bit of a change in plan, what with the lockdown at the moment.
Yeah, so Sam is helping me right now to run a model. Well, he's doing the model and I'm telling him what to run, and so this is looking at whether we can find the temperature and pressure regime of the material that would be impacting Phobos, so whether we can come up with a prediction from that of what should survive, what biomarkers would survive this temperature and pressure regime. And then the idea would be to test that with my impact experiments. So I'm going to make the projectiles, hope that they work, then I will fire into a Mars source rock and collect the ejector, then subject it to the heating, flash heating for going up through the atmosphere, and then fire this ejector into Phobos. So it's this series of impact experiments. So it's going to take me a while. I think I've got a good year or so of experiments. So this particular situation hasn't helped that. But yeah, I'm going to be in the lab a lot. And then I want to continue in research. I want to continue and do a postdoc and probably continue more into the planetary protection side of things. Astrobiology was not something I thought I would go into when I started this PhD. I just wanted to use the gun, really. Gun, cool, do impacts. And astrobiology is becoming the reason why we do this science now. It's where the money is, and that's the main goal, is to find life in the solar system and beyond. So it's applying impact studies to astrobiology. So that's what I'd like to do in the future.
Yeah, I mean, I'm going to continue with this work with Zoe. Not only looking at the kind of the Martian, the ejection of Martian material and the survival on Phobos, but hopefully we can model some of the impact experiments themselves and try and compare almost a benchmark between how accurate these models are looking versus the experimental studies, and then apply that to how accurate that might be for actual impacts into Phobos. So that would be interesting to kind of do an experimental model analysis. That'll be really good. Alongside that, I'm hopefully going to finish up some of this terrestrial meteorites and modelling into the moon as a paper, and then continue on to what was actually the main focus of my PhD from the beginning, which was carbonaceous chondrites. So I never actually meant to get into biomarkers or astrobiology either. My PhD was originally based on carbonaceous chondrites into the moon and their resources for in situ resource utilization. So that will be the next stage of my PhD in modeling those kind of larger impacts, kilometer-sized impactors, and how the constituent elements such as carbon, nitrogen, things that aren't very native to the moon, and whether they're in large enough quantities that they could be used for a sustained lunar presence for human activity.
I had no idea that you were working on that as well.
Trying to begin it, but it's kind of getting past this interesting thing that I found out with the modelling of terrestrial meteorites, and that kind of has been my past year or so. Moving on to the actual part of my PhD would be, I mean, it's not like I haven't enjoyed this part of astrobiology. It's been an interesting side thing, but it's not the main focus of why I went into it.
So you said you've both somehow forayed into astrobiology. What was it that made you choose to do a PhD in planetary science in the first place?
Okay, I'll go first. So I did my A-levels at Hillsborough in Cambridge, and I did geology. I was lucky enough to do geology as an A-level. And at the very first page of the book was about planetary science. And I was like, I want to do this. And within those 2 years, I was like, come on, I want to go and do a degree now. And then I started at Manchester doing geology with planetary science, and that was the only place to do an undergraduate in planetary science. And that's where I studied with Katie. And then I did a meteorite project for my third year project, looking at how you could have metal in a lunar meteorite and how this could be a meteorite that has landed on the moon and has been preserved in the regolith and then has created another meteorite to fall onto Earth. So sort of a similar thing to what Sam's doing and what Tom's doing now. So it's that I loved it. In the very first year of my degree, I knew I wanted to do a PhD. It was instant. But I didn't know necessarily what, and I wanted to do something to do with impact, but you can either look at modelling, and I'm not a very good modeller, I can't do coding, or you can look at impact products, which is with meteorites. But then I didn't know that there was this thing in between, which was doing experimental work using a light gas gun. So I went down to Kent and did an internship with their light gas gun, and I just loved it. It was great to be able to actually make these craters that you're studying is brilliant. So I knew I wanted to do that, and then just by chance the OU was offering a PhD using the light gas gun. So it's a little bit of it's luck really, because no one else has used the light gas gun before me. There aren't any other PhD students at the OU currently. There's now one has just started, and there will be some in the future, but before me there wasn't. So it is luck of being able to go and do that.
Yeah, I mean, it's funny, it's a similar route to me as well. I did A-level geology as well, and it was undoubtedly my favorite subject at the time. That kind of spurred me on to going to do an earth science undergrad, which I started at Glasgow but actually finished at the OU, which is a funny kind of coincidence. But Zoe and I have these weird kind of crosses, it seems, in paths. And so from that, I went on to do a UCL master's in planetary science. And that's when I really found kind of this path that I wanted to go on into impact studies as well. My master's thesis was on numerical modelling of Martian impact craters and kind of the effect that ice has on them, the morphology of the craters. And that modelling kind of aspect really kind of took me in the idea of you can get data straight out of this computer model and then apply it to what you actually see on the Martian surface. So a combination of kind of remote sensing and modelling was really interesting to me. And from that, I initially wanted to go for a PhD to do with the Martian landing sites for Mars 2020. Didn't get that one, but then went and applied at Birkbeck for this one that came up on what happened to be numerical modelling of impacts into the lunar surface, which I thought was kind of serendipity almost. It was perfect for what I'd done previously. And that, yeah, it kind of went from there. That I started with that, and it just kind of was the fit for me at the time. And funnily enough, Zoe and I went for the same PhD initially.
I thought you weren't going to mention that because clearly he got it and I didn't. But
look where we are now.
I get to use a gun.
You do get to use a gun. I don't get to do that.
No, I think it's great. I think it was the chances of these two projects to be presented at the same time that sort of consider the same thing of how impacts can deliver material from one place to another. It's really interesting. So it's nice that we've been able to go through the PhD process considering the same thing but in different scenarios, but working almost together up to a similar goal of trying to find the answers for this. So I think it's fun.
Yeah, it's so strange. I knew when I asked the both of you that you were both doing quite similar projects, but it wasn't until talking to you today that I realised how much synergy there is between them. But that's great to have someone doing their PhD at the same time and being able to share this much stuff.
Yeah. Power of collaboration.
Exactly.
Mm-hmm.
It would be silly not to collaborate. So why not?
Yeah.
All you need is a global pandemic to prevent me from going in the lab to say, Sam, will you help me? Do some modelling for me, that'd be great.
Yeah.
Well, we are not done yet. We have one final question that we ask all of our guests. If you could be doing anything else, sky is the limit, either in academia or outside of academia, what would you want to do?
Ooh, big question.
I have an answer. I love flying. I'd love to be an airline pilot. I'd started doing a few lessons. You could learn to fly from the age of 12, which is really bizarre. So I had maybe it was 11, maybe it was 12. I don't know. I had my first lesson when I was 12, and I think if I become rich, then I will continue and get my pilot's license. And yeah, that's a number 2, but I think it requires you to be rich before you can do it to pay for the lessons. But that'd be great.
Wow, okay.
Yeah, that's awesome. You fly your own private jet around.
That'd be great.
Yeah, what did you get to do in the lessons then?
So it's a lot of just control and feel. It's like driving a car, really. You just have to feel where you are and feel how the atmosphere around you is affecting the plane. And I think it's the same as driving a car, really. It's about feel, but it takes, I think, many more hours to learn. And I'd love to go back to that. And yeah, it'd be great.
Cool.
Mine, I think I'd love to be a musician. Not like a super successful, like massively famous musician, but someone that's like found a really nice niche and gets enough money to kind of live off comfortably. Because the idea of fame kind of scares me, but to do music every day and to kind of be successful at it and have people listen to it would be amazing. I'd love that.
Yeah, it's cool. Do you play anything?
Predominantly at the moment just playing guitar and singing. Yeah. But a few instruments when I was younger as well, that like drums and piano and things. But not so much anymore. Not in this house. Neighbours will not like.
I like the idea of you asking that question of like, you want to be a musician, but do you actually play anything? I mean,
it's just very aspirational.
Yeah.
I like the idea of it.
It's a nice idea. Yeah.
Amazing. Well, yeah, I love asking people that question. As long as it doesn't make them go, actually, you know what? Forget my PhD.
This is my dream now.
Follow your dreams.
If that happens, then that's on us.
Yeah, exactly. Well, thanks very much, you two. I think that was a really good episode, and it was wonderful to chat to you.
Indeed, yes. Thank you both very much. But yes, so thank you. And for all you in the audience, thank you very much for listening. If you want some more Earth and solar system content, do check us out on all the social medias everywhere, from Twitter to Facebook to Instagram. We're at Earth Solar System. All the links will be in the episode description. But in the meantime, I hope you all have a lovely week, and we'll see you next time. Bye-bye.
Bye.